Good evening, everyone. Welcome to the sixth session of problem solving for the course Structural Analysis 1. So today we'll be looking at statically indeterminate structures, how to determine the degree of static indeterminacy, and what are the methods available to analyze statically indeterminate structures. So basically we can divide them into two types. One class of methods is called force methods, and the other class of methods are called displacement methods of analysis. So first, in this course, we'll be covering uh, force methods of analysis. So in today's session also we'll be solving a few problems based on the force method. This I hope helps you solve the assignment number 7, which is due this week, Wednesday. Let me start sharing my screen. I hope the screen is visible and my voice is clear. Okay, so let me start. So let us start with a brief introduction before we get started with the problem. So today we are going to look at statically indeterminate structures. So um, just a minute. So by now, all of you must be familiar with what are statically indeterminate structures. So how are they defined? Can any of you answer? What are statically indeterminate structures? So these are the structures in which the number of unknowns is greater than the number of static equilibrium equations. Is that okay? Is my voice audible? Hello.
Audible, sir.
Okay, thank you. So yes, we call those structures for which the number of the unknowns can be determined only by using the static equilibrium equations. Those are called statically determinate structures. But in most structures in civil engineering, the number of unknowns are number of force unknowns basically. So number of unknown forces or reactions. Forces or reactions. In most civil engineering structures, the number of internal forces or reactions which are unknown a priori, the number of such unknowns is greater than the number of static equilibrium equations that are available to solve the problem. So in this case, these alone are not enough to solve the problem. We need something more. So such structures are called statically indeterminate structures. Now, why are they more common? Let us look at the advantages of statically indeterminate structures. So why do we use statical indeterminate structures in civil engineering? The first reason is the maximum stresses and displacements in a statically indeterminate structure are less than that in a statically determinate structure. Why is that so? It is because we have additional support reactions that reduce the displacement. For example, if you take a simply supported beam, it's going to deflect something like this. Suppose the beam has length L, width W, and height H. But the same beam, if you make it so this is a statically determinate structure, but the same beam, if you either put an intermediate support like this, it's going to deflect like this. So here, when the maximum deflection is delta, here because of the reduced plan, it will be much less. And also there is a hogging moment that comes onto this. So here the displacements will be less and the stresses will also be less. Similarly, if you make it a fixed beam, which is also statically indeterminate, again, the maximum displacement will be reduced only so much. Well, the reason is again hogging moments that are generated here. So the maximum stresses and maximum displacements in a statically indeterminate structure are in general less than a statically determinate structure. Second thing is statically indeterminate structures have redundant members. So when they have redundant members, if there is an accidental overloading of the structure, right? If suddenly because of some issue or some some fault in the structure, suppose accidentally it gets overloaded, suppose the structure gets overloaded, then redistribution of forces occurs. So if a structure is statically determinate, say for example, if you take a simply supported beam and it is subjected to a certain load, but for some reason, if load exceeds the collapse capacity, which is if it exceeds the maximum design load, that is the maximum load it can take, then what happens? Immediately, it forms what is called a plastic hinge. So we know if it is a statically determinate beam, we know the maximum bending moment is something like this. Assume it's a steel beam. So here you have the maximum bending moment, which is WL squared by A. So at this section, if you take, say, if the beam is something like this, as the load W is gradually increased, the stresses in this section will be linearly distributed. At some point, this stress, the maximum stress, will yield the yield stress. And further, upon increasing the load, what happens? The entire section becomes plastic. Once the entire section becomes plastic, it has no more load carrying capacity. So what happens is, as the deformed beam, which is something like this, develops what is called a plastic hinge. So this acts as an internal hinge, but while carrying a moment of m. Beyond that, it cannot take any incremental loading. So what it does, it simply collapses. On the other hand, if you take this beam, which is statically indeterminate, if you take a statically indeterminate beam, so this is a mechanism. As I explained in my first session, there is no longer a structure. Upon adding any incremental force, it accelerates. It cannot take the load and transfer it to the support safely. So it becomes a mechanism and it is useless. On the other hand, if you take a statically indeterminate beam, say the fixed beam shown here, in that case, what happens is, you add some more space. So the statically indeterminate beam, what happens is, suppose that is also subjected to a uniformly distributed loading W. Then what happens? You have hogging moment at the supports and some sagging moment in the midspan. So later you will know that this is equal to WL squared by 12 and the middle value is WL squared by 24. So where will the first yielding occur? Because this moment is higher than what is happening at the midspan. The first yielding will occur at this spot. So here, same thing happens. So there will be a linearly dependent strain distribution, stress distribution. Then once it starts yielding, the topmost fibers and the bottommost fibers will yield. Then as we increase the load further, the entire section undergoes plastification. But in this case, what happens is, even if these two become yield plastically, they'll be supporting a moment. It will be in the reverse opposite direction. They'll be supporting a moment but the middle would still not have yielded because the moment here is still only half of the value at its ends. So the beam continues to take load, although the yield has occurred. Although two plastic hinges have happened, the beam will continue to take load. So that is the benefit of statically indeterminate structures. So since there are redundant members or either there are redundant members or redundant reactions. So at the time of design, although we'll consider all the loadings. For that loadings, when we add more members or more reactions to support than what is required for just the stability of the structure, it helps when there is a overloading of the structure due to some fault. So accidentally, if the structure is overloaded, it ensures the static indeterminacy ensures that the structure doesn't collapse in a catastrophic manner. So these are the two main advantages of statical indeterminate structures. But there are also disadvantages. So what are the disadvantages of statically indeterminate structures that you can think of? For example, if we have a simply supported beam, and suppose this support is sinking by some angle, some delta, okay? It can sink. So for example, in real, suppose you have a bridge, you have piers like this, which have some foundation. And the bridge deck is most often simply supported. So they'll put a small uh, cushion or something, bearing, and then the bridge deck is most often simply supported on it. No, because of some issue, say the soil here is suddenly becoming weak, and if this support sinks a little bit, say it goes here, what happens? The bridge deck just rotates. So if the support sinks, what happens is, if it is simply supported, it simply rotates this way. So since it is a rigid rotation, it doesn't generate any internal stresses. So that is the benefit. So if you have a statically determinate structure, if there is a displacement or rotation that is imposed on the support, the structure does not generate any internal stresses because the supports are just enough to hold the structure in place. They are just enough to add keep it in equilibrium. Okay. But suppose the same thing happens in a statically indeterminate structure. Say if we have a fixed beam, and say this support is sinking by some delta, then what happens? Since this maintains the 90 degrees here, it will deform this way. Now, since it is deforming, there will be strains and there will be internal stresses. So these internal stresses are not what we designed for. We designed it for the applied loading. But because of unexpected support sinking, there is a extra internal stresses that are generated in the structure. So this is a major disadvantage of statically indeterminate structures. So not only in this, even if you take a continuous beam, if you have an extra support in between, and say this support is sinking, what happens? The beam bends this way. Because this support is not sinking, there will be tensile stresses generated at the top and there will be compression. So it is generating unexpected internal stresses because of the redundant member. So that is a major issue with statically indeterminate structure. But in spite of it, it is very often used in civil engineering because the advantages are more than the disadvantages. Now let us get to the methods of analysis. So how do we analyze the structures? Okay. So we have already seen that so how do we analyze them? So we have already seen that the number of equilibrium equations the number of unknowns are greater than the number of equations, which means we need more equations. What gives these extra equations? That is a condition called compatibility. And what is compatibility? Yes, Sumit?
Sir, good evening.
Yeah. Please tell me.
Actually, could you please explain that point regarding uh, the the determinate structure, the non-sinking property of that what you have shown on the last slide of the roller support. I didn't get that actually. Could you please
Oh,
explain
yes.
it?
Yes, sure. So what I said is, suppose we have a statically determinate structure. Right? Say if we will take a simply supported beam.
Okay.
And suppose the soil below this support becomes weak because of some reason, waterlogging or whatever, and say this support is sinking by some delta. In that case, what happens? The beam just rotates.
Okay. Okay.
As it rigidly rotates, it does not generate any internal stresses because rigid body has no strains, right? Not rigid body, rigid
Okay.
motion. Rigid motion does not induce any strains. Similarly, if you take a cantilever beam,
Okay.
because of some reason, suppose this support is starting to rotate, it is not standing straight. Say, suppose because of some reason, if this support is rotating, again, it rotates rigidly. This does not bend. Or if this support is sinking by some delta, then the beam just translates rigidly.
Okay.
So that is the benefit of statically determinate structures. In case there is an accidental, unexpected sinking of the support or some unexpected rotation of the support, then no strains are induced. Not only in this just simple case, even if I take a beam, right?
Portal
Sorry,
frame.
it is portal frame. Suppose this starts sinking by some delta, then nothing will happen. The portal frame just rotates rigidly.
Okay, sir. So what I understood is
Yes.
the sinking, sorry, the rotational motion or the rotation of the rigid body does not induces any strains. Am I right?
Yes. Rigid rotation. Rigid rotation means so the when do strains happen, right? When do strains happen? When if you take a small section of the material, if so material will have some points, right? So suppose these points are moving relative to this point, there is a change in the distance in between them, and that causes strains. But in
Okay.
rigid rotation, when the structure moves as a rigid body, what happens? So by definition, rigid motion means so by
The fiber
definition,
distance does not
uh,
change.
the distance between different points,
Okay. Okay.
distance between points remains the same. So
Okay.
if the distance between the different points remains the same, then there are no strains induced. So that is the idea. So in a statically determinate structures, no strains can be induced by a sinking support. But in statically indeterminate structure, it is they are generated. That is why even today, while all our buildings are all statically indeterminate to a very high degree, bridges are always designed as most bridges, highway bridges are designed as statically determinate structures. So that's what I drew
Simply
here.
supported.
Yeah,
Okay.
they're all simply supported. The bridge deck is simply supported on the pier. And to ensure it is actually simply supported, they don't put it directly on it. They'll put it in a small bearing so that it allows
Bearing.
free rotation.
Yes. Yes.
So that is the idea. Is it okay now?
Yes, sir.
Okay.
Actually,
Okay. So
I am also a professional. We
oh,
work
okay.
in infrastructure industry. Actually.
Okay. Thanks. Good to know that.
Okay.
I have some more space. So coming to this point, um, I was saying that the number of unknowns are more than the number of equations, and what we need extra is compatibility conditions. So what is compatibility? It is nothing. It is very simple. It means the various parts of a structure remain uh, remain fit together, right? This may seem very vague, but it basically means there is no breaking or no overlapping. That is, if you have some structure like this, some structure like this, can be anything. So let me take a proper structure. Some total frame like this. While analysis, what I should ensure is that all parts are connected. So if my solution is such that if the displacements I get are such that this happens, then it is invalid. Or similarly, the example that Sir explained. If you have an arch, a statically indeterminate arch, the condition is these supports are attached to the arch. That is, the arch is attached to the ground through these supports. The horizontal reaction is indeterminate in general. When we apply a vertical load, the horizontal reactions are indeterminate. Only thing that we know is they must be equal and opposite. But if it turns out that I get such a horizontal reaction which makes my arch go like this, then it is wrong. Or this is kind of breaking off. Or if there is a solution that makes my arch overlap with itself, something like this, right? That is also. So what we expect is, in addition to in addition to satisfying the equilibrium equations, we also expect the structure to behave in a sensible manner. That is, the different parts shouldn't overlap each other, or they shouldn't break while doing a linear elastic analysis. If the structure actually breaks, that's a different story. That happens if you're doing damage analysis and those things. But what we do is a linear elastic analysis. So under linear elastic analysis, we don't expect a structure to overlap itself or different parts to break out. That is basically compatibility. So these conditions these give extra uh, equations to solve the problem. How many equations it gives? That will determine by static indeterminacy. Now let's see what is static indeterminacy. So we have already seen that in statically indeterminate structures, there is minus the number of equations is greater than zero. There are more unknowns than the number of equations. In this case, what happens? So it is greater than zero. Now the difference itself, let us call it as, so this difference itself, let us call it as degree of static indeterminacy. So how many extra conditions or equations are needed? That is degree of static indeterminacy. Fine. Now let us see an overview of the methods that we are going to see. So now we know that we need extra conditions. So for solving this problem, we can take two approaches. One is force method, and the other is displacement method. So we need more equations, but what gives those extra equations? In force method, forces are unknowns. So F is unknown, forces in different numbers are unknown, and the extra conditions are given by compatibility. So compatibility gives extra conditions. This is about force method of analysis. So this is the traditional method. This is old. Nobody uses force methods in practice today. So what people adopt in computer because the actual structures are so big that people do only computer-based analysis. So this is modern. So finite element method, if you have heard of, is based on displacement methods. In this, the displacements are unknown. So delta is unknown.
So the STAD Pro software also uses displacement method.
Yes, yes. Whatever software you can think of, they're all based on finite elements. And what is common in finite elements is displacement-based finite element method. So all modern software, they use displacement method of analysis. One such displacement method of analysis is actually FEM is finite element method is much beyond displacements, but it is also for structural analysis, you can consider it to be displacement based method. Now here, the primary variables are the displacements, and what helps us solve for these unknown displacements is equilibrium equations. Equilibrium equations give extra conditions. Of course, in both cases, we need force displacements. So here also we need force displacement relations. Here also we need force displacement relations for a member. That is needed in both cases. Then what else? Fine. Now how many extra equations? So then what else is common in between both is both of them result in a linear algebraic system of equations. When you're doing linear elastic structural analysis, both of these methods result in a linear algebraic system of equations. So what is system of equations that you must be aware of? So you get normal, like if you have a 2 by 2 system, you have a11 x1 plus a12 x2 is equal to b1, a21 x1 plus a22 x2 equal to b2. So if it's a small 2 by 2 system, you know how to solve it, right? You can use Gauss elimination or Cramer's rule or something and get the unknowns x1 and x2. You can always express this as a matrix form, as a x equal to b, where A is the matrix a11, a12, and so on. X is the vector of unknowns, and B is a vector of knowns. So both of these methods end up in some algebraic system. In this algebraic system, in the force method, so in the force method, the algebraic system, what you get is the unknowns. As I said, in the force method, the unknowns X are unknown internal forces. What are B? B will be no displacements, constraints. So as we saw in the arch example, the constraint there will be that both the supports are not going away. That is, the supports are the particular support is fixed. The displacement of the support is fixed. So known displacement constraints, right? This kind of is captured by the vector B, which is a known vector. And what is A? A is a special matrix called flexibility matrix or matrix of flexibility coefficients. Flexibility matrix. This is the force method. And in displacement method, what we have, X will be the unknown displacements. X will be the unknown displacements. What will be B? B will be no applied forces. And what will be A? A will be called stiffness matrix. So it is very simple. So this is what we do. So for example, if you take a small spring, uh, suppose you have some mass and you're applying some force F, this is X, this is K. Now if you have to solve for the unknown X, how do you do it? So you put K X equal to F. So if you're subjecting it to a known force F, and you want to solve for the unknown X, if you take this X itself as unknown and you solve it this way, what is this called? Stiffness. This is the displacement and this is the known force F. Suppose you want to solve using the force-based method. So this is displacement method. Suppose you want to solve it using the force-based method. In that case, how will you do it? You know that there is an applied, suppose you take, there is an unknown force F in the spring and the flexibility of the spring is 1 by K, right? If K is stiffness, 1 by K is the compliance or flexibility. And here you are applying a, say, displacement, some delta. In this case, you relate it as 1 by K F is equal to delta. So this is called compliance or the stiffness. 1 by stiffness is called compliance or the flexibility. And F is the internal force, which is unknown. And delta, if you are applying a known displacement constraint, it is known. So this is basically force method and this is the displacement method. Now, what are the size of this matrix? Now, how many internal forces you will have when you're using force-based method, right? So the number of unknown internal, so known internal forces, you know, but how many unknowns you will have? That will be exactly equal to the static indeterminacy. So when you're not able to solve a problem, you will assume some of the internal forces are unknowns. Now, how are these? How many of these unknowns are there? That will be the number of that will be equal to the degree of static indeterminacy. So A, the flexibility matrix in force method will be a NS cross NS matrix. So how many equations you have? So if you have NS unknowns, if you have the static indeterminacy, if it is equal to NS, then you need NS equations because only if it is a square system you can solve. If it is a rectangular system, you can't solve. You need NS number of compatibility conditions. So NS is equal to unknown forces and it is also equal to the number of compatibility conditions that are available. So it's also equal to the number of compatibility conditions that are available. Similarly, when you see the displacement method, so the displacement method, if you have unknowns, say number of kinematic, the number of unknown displacements, which is equal to the kinematic indeterminacy, right? So I haven't defined it yet. So what is kinematic indeterminacy? Let's go to that.
Sir, sorry to interrupt.
Yes,
But,
yes.
I mean, the compatibility equation means boundary conditions, right? No?
Compatibility. Okay, in a general sense, compatibility means what I said, that the structure doesn't overlap or break off. In structural analysis, people often use compatibility to to refer to this ensure that the boundary conditions are properly applied. So, to consider something like this,
Okay, okay.
when you say it is subjected to some load, and if you just take the static equilibrium equation, something will be unknown. You can take this force as unknown. So it is basically something like this. There is a condition on this force which it should satisfy so that this will be in equilibrium. That is fine, but that is not enough to solve the problem. In this case, if that alone, if you take an incompatible solution field, what will happen? You will get a displacement field which results in a structure like this. So
Okay, okay.
basically, it means that the support has broken off from the structure. That is what I meant. You're right. You can say compatibility means that the boundary conditions are properly enforced. That is correct. But compatibility is even beyond that. Not only that, this solution is not acceptable,
Okay.
even this solution is not acceptable according to compatibility. That is what it means. So here the boundary conditions are correctly enforced, but in between there is a breakage. This is also not acceptable.
Okay. Okay.
So I was saying
Uh,
that yeah, I was saying about kinematic indeterminacy. So we define degree of kinematic indeterminacy. Basically, it means unknown degrees of freedom. Now, what are degrees of freedom? Degrees of freedom of a structure are the number of internal a number of variables or parameters. Okay, how many variables or parameters that can completely specifies the configuration of the structure. So if you have a skeletal structure, right? What is a skeletal structure? A skeletal structure means it looks like it is jointed at many points, and it is consisting of some members, straight or curved members, but basically line like members. They don't look like a plate or something. So it is composed of such the members that just look like some uh, line segments. So this is called a skeletal structure. So in skeletal structures, if you know the displacement of the joints, if you know the displacements and rotations of the joint, you can determine you can determine the internal displacements and rotations by using the uh, static equations of equilibrium. So it is sufficient to consider only the degrees of freedom at the joints of the structure. So joints are also often called nodes in structural analysis. So if you know what are the uh, displacements and the rotations at the nodes, you can determine the entire displacement field of the uh, member in between the nodes, provided the loads are applied and it is in equilibrium. So in skeletal structures, the number of unconstrained degrees of freedom or unknown degrees of freedom, we call it as degree of kinematic indeterminacy. For example, if you take a two-story building like this, so and it is having so many joints 1, 2, 3, 4, 5, 6. These are all idealized as some beam elements, beam members. Okay, these are all beams and columns. So, so what all can happen here at 6? Can the point 6 move or rotate? No, because it's fixed. At 5, what can happen? This can move this way. This point can move upwards and it can also rotate. Similarly, 4 can move upwards, it can move rightwards, it can rotate. Same thing applies to this and this. And at point 1, what do we have? So here you can have all this. At point 1, it cannot move, it can only rotate. So all these are unknown without knowing the equilibrium equations for this structure. So these are all kinematic indeterminacies. So these are also known as an admissible displacement. Okay. So these do not violate the boundary conditions. So if I specify any I can specify any value for these displacement quantities. So for example, theta 1, u2, theta 2, v2, all these can be specified arbitrarily without violating the boundary conditions and the compatibility. That is, these are all connected, not overlapping. So I can specify these without any issues. Uh, so these are but yeah, these can take any value without violating compatibility conditions. So they are called degrees of freedom. I'm free to specify these values without violating the compatibility conditions. But any arbitrary value assigned to these degrees of freedom will violate the static equilibrium equations. So if we have nk unconstrained degrees of freedom. Unconstrained degrees of freedom. That is, I can specify nk of them without violating the compatibility conditions. Then I need at least, not at least, I need exactly nk equilibrium equations to determine them. So in the displacement method, the matrix system that we get will be, so this is displacement method. In that, the matrix we get will be nk cross nk. There will be unknowns. How many unknowns? There will be nk unknown degrees of freedom, and the number of equilibrium equations we have, right? Then that will be also equal to nk. So this is the crux of both this displacement and force-based methods. Now let us quickly get into the problems for today. Now there are some shortcuts to determine the degree of static indeterminacy for any structure and also the degree of kinematic indeterminacy. But I would like to warn you that these shortcuts may not always work. As we will see in some of today's problem, you need to think beyond these shortcuts to solve the problem correctly. But however, in most general structures where there are not many issues, not any exotic member in between, you can say that the degree of static indeterminacy, we can always split it up into external indeterminacy and internal indeterminacy. What is the external indeterminacy? Externally, how many equations we are falling short of. That is, if there are n reactions, suppose if there are r number of reactions, for the full structure we only have 3 equations of equilibrium, force balance in x, y directions and the moment. So the degree of static indeterminacy, which is external, is r minus 3 for a 2D structure. 2D structure. And what is NSI? This depends on the type of structure. If you have a truss, how many equations you are falling short of? If there are m number of members, the forces in each of the members is unknown. So you have m unknown minus how many equations you have? You have 2j equations, the vertical and horizontal equilibrium of every joint. So there are 2j equations, but are they enough? But those 2j equations will also include these 3 equations for the whole structure, right? If every joint is in equilibrium, it means the entire structure is in equilibrium. All the internal forces will cancel off. If you add all of it, you won't get a new. You will not get a new independent equation. You will get something like x plus y equal to 3 and 2x plus 2y is equal to 6. Suppose if you're given this system, is it enough to solve for x and y? No, because both are actually same. So same thing happens here. If you enforce the equilibrium of every joint in a truss, and if you add all of them, it will not give an independent equation. They'll be linearly dependent. So you need to subtract the 3 equations that you'll get by overall equilibrium of the structure. So in a truss, the degree of static internal indeterminacy is given by m minus 2j minus 3, which is m plus 3 minus 2j. And if it is a frame, it is given as 3c, where c is the number of closed loops in the frame. I'll explain why it is so when we solve the problems, but right now you can just take it as given. Nk, as we already defined, it is nothing but the number of degrees of freedom minus the number of support restraints. So we'll see in the problems that these shortcuts don't work always, but they are useful in most of the cases. Now let us go to this problem. So let me zoom in a bit. Calculate the degree of static indeterminacy and the kinematic indeterminacy for the following pin jointed structure. So basically this is a truss. Now let me
Hello.
yes. Yes, Sumit.
I remember one formula during
Yes,
my engineering for
yes.
that frame structure. It was something like that: m minus 3j plus 3 minus number of uh, internal reaction generated due to internal support or something. Am I correct? Am I getting it or not? Please correct
Uh,
me.
yeah, let me think about it. If you're having m minus 3j,
We considered 3 degree of freedoms at each support at each
at the
joint,
joint. Yes, yes, that is fine.
plus 3 minus number of reaction generated due to internal hinges or something like that. I didn't.
Yeah, that should also be fine. I think so. Uh, Basically,
Uh,
there
uh,
are many ways to do it. So you can consider that also. Let me tell you how that comes. Right? So
it has been many years. I think 7 to 8 years almost.
okay, okay. So what you're saying is, if we have m members and j number of joints, uh, the member forces are unknown. But I don't think it should be m minus 3j. It should be probably 3m because every member has an axial force, shear force, and a bending moment. So it is
Okay.
probably 3m. Uh, and the number of joints will be, say, as you said, 3j. Uh,
Uh,
that seems okay. Uh,
3m. Okay.
yeah,
Okay.
3m minus 3j, that is fine. This is internal, right? This is internal. But
Inter.
again, you should exclude if every joint is in equilibrium. Again, you will have the uh, you will include the global equilibrium equations. You have to subtract this. This is internal, and plus external, you will have r minus 3. So if you add both, so internal, I think you're right. M minus 3 into m minus 3j. You said m minus 3j. That is not correct. 3m minus
Okay.
3j plus 3 is okay. But I'll tell you how it is
Okay.
equal to this closed loop, right? If there are only open loops in the structure, if you have only open loops in the structure,
Okay.
then
Okay.
the number of members will be equal to number of joints, right? If you have only open loops in the structure, the number of members will be equal to number of joints plus one. Sorry.
Plus 1. Okay.
Yeah. So the number of members will be equal to number of joints plus one. So here I can write this entire thing as 3 into m minus j. Uh, sorry, not plus one, minus one. So there are 4 joints here, and there are 3 members. So this you can write it as m minus j minus 1. This one. If there is one closed loop, right? If I put one more member here, then the number of members is j minus 1 plus 1. And if there are 2 closed loops like this, then the number of members is j minus 1 plus 2. So what is this extra? This is just equal to c. So you can write m minus j minus 1 as equal to the number of closed loops. If there is one loop, then there will be one member extra. If there are 2 loops, then there will be 2 members extra in addition to the number of equilibrium equations. So that is how I got this 3c. What you said is also fine. You can also do 3m minus 3j minus 3. So both are fine. Is that convincing?
Yes, sir. Yes.
Okay. Now let us go to this. So this is basically a truss structure. So let us first find out the external indeterminacy. Let me call it NSE. So how many reactions we have? We have an upward reaction. We have a horizontal reaction. We have an upward reaction. We have a horizontal reaction. So we have 4 reactions. And how many equilibrium equations we have? 3. So 1. Now let us find internally. Before we go to that, let me ask, is this internally stable? Is this not internally? Is the structure stable?
I think
If you if you
it is
apply a
unstable
force,
actually.
yes, that is where the issue is. It is not totally unstable. So if you take this part alone,
Okay.
if you take this part alone, and you apply forces like this, it will accelerate. It will just go like this. So it is internally unstable.
Okay.
Why do I say this internally? Because now you see the structure with its supports. Now if I do this, this is not free to go to the right. So this will also shorten. This member will also shorten. This member will also shorten. So there'll be compressive forces in these members as I try to do this kind of thing. If I take this, if I isolate it from the supports, then it is internally unstable. It's not like a usual truss. But since I have extra supports, since there is an external indeterminacy, this structure is actually stable. So if you see, along with the supports, if I subject it to some forces, it is always stable. There cannot be a mode of deformation where the members are not stressed. So along with the support, if I say, it will be stable. So let us find out the degree of static indeterminacy internal. So internally, how many unknowns I have? One unknown in this member, one unknown in this member, one here, one here, one here, one here, one here, and one here. So there are totally 8 members. And how many joints do I have? 1, 2, 3, 4, 5, 6, 7, 8.
4.
Wait, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6,
6.
7, 6.
6.
So 8 minus 2
into
into
6. 6 plus 3.
wait, there are 8 unknowns. 2 into 6 minus 3.
Plus 3.
So it is minus 1. So
Plus
internally,
1.
it is. So this shows that it is actually internally unstable. We have more equations than the number of unknowns. That is what it means. So but together the total degree of static indeterminacy is 1 plus minus 1, which is 0. So it is a stable, statically determinate structure. Again, there is an issue. Although the static indeterminacy, degree of static indeterminacy is 0, can we solve for the unknown reactions? We cannot solve for the unknown reactions directly. So that is an issue. We have to consider the internal. So if we just isolate the structure from its support and apply the unknown reactions, we cannot apply the global equations of equilibrium, the 3 global equations of equilibrium, and solve this. So that is an issue. We need to find the internal forces to solve it. So the degree of static indeterminacy for this structure is 0. Now let us come to kinematic indeterminacy. That is much simpler. How many? Let me erase all this and let me draw the kinematic degrees of freedom. Now can I draw a rotation here? No. What is the reason? Because in a truss, all the joints are hinge connected. They are free to rotate. So if a hinge acts like a point. So even if it rotates or even if it doesn't rotate, it remains the same. It's not like a joint. So if you have a joint, if it rotates, it becomes like this. And that induces strains in the member. But if I rotate this hinge, it is not going to induce strains in the member because the members are not attached. They are just hinged at that point. So that is the significance. So even if I impose a rotation at the joints, it is not going to induce any strains in the member. So that is not really a degree of freedom for this structure. So only degrees of freedom I have are the translation at each move. So here, is there any degree of freedom? No, it is vertically restrained, horizontally restrained. Here it can move up and it can move right. Here it can move vertically, horizontally, vertically, horizontally, vertically. So the degree of kinematic indeterminacy for this structure is 8. Let's check the answer. So static indeterminacy is 0, kinematic indeterminacy is 8. So the correct answer is D. Yeah. Let's go to the next question. So choose the appropriate option for static indeterminacy of this following truss. Again, let us the external counting. So what is the degree? So how many reactions you have? You have one vertical reaction, one horizontal reaction. Here you have one vertical reaction, one horizontal reaction. Here you have only a vertical reaction. So totally NSE. Externally, you have 5 support reactions, and how many equations of equilibrium you have? 3. So external indeterminacy is 2. Let us go to internal. So how many internal members you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. There are 21 internal members. Each of them will have one axial force, which is one unknown. And how many joints we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Minus 2 into 11 minus 3. So, wait, are there 11 members? 1, 2, 1, 2, 3, 4. Yeah, fine. There are 11 members. And here you have, so 2 into 22 minus 3 is 19. So there are 2 redundant members. You can also easily find out what are the redundant members. So this is one extra member, this is an extra member. If you remove those, you will get a statically determinations. Actually, you can remove any member, but this actually you can see it spoils the pattern. Usually this is a very famous type of truss. These 2 are extra members. So what is the total static indeterminacy? This 4.
Sir,
Is
actually, I want to ask whether we can consider the intersection of the bracing members or the diagonal members as a joint, pin joint or not. Actually, not
no.
pin joint, uh, just a joint because we connect it through a plate. Na?
Yeah, that's why they have mentioned in the question that diagonal members are not connected to each other. So in 3D, if you see this, you will have, say, you will have a gusset plate like this.
Yeah, gusset plate.
I'm drawing this one. I'm drawing this one. So this is going like this and connected to another gusset plate like this. Similarly, here you are having a gusset plate. Suppose you weld it on the opposite side.
Okay.
So there's no connection between. It's like this. Usually, they don't do such things in design. This is just for a textbook problem. So
Okay.
it's
Yes.
not connected means you they are not touching each other. That's what it means. So I weld it on the opposite side of the gusset plate. Usually it's always in both the directions to avoid torsion. Right? Always they put double angles. But in this case, you can think of a situation like this, where the diagonal members are not connected to each other. If otherwise, if the diagonal members are connected and there's a gusset plate in between which is connecting all 4 members, then it is statically determinate. Internally, it is not indeterminate. But this problem is different, so it's different. So let's go to the next one. Determine the kinematic indeterminacy of this frame. So if you look at it directly, you may get a wrong answer. That is, let us see. Let us mark the reactions. So totally, how many joints we have? 1, 2. It's a frame structure. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, if there are no supports, if there are no reactions, if the structure is just free, in that case, how many unknowns we'll have? We'll have 3. We have vertical translation, horizontal translation, and rotation. We'll have 3 into 11 equal to 33 degrees of freedom. We'll have all constrained plus unconstrained put together. But how many constraints are coming? Now, what are the constraints? Let us list them out. The horizontal reaction is equal to the vertical. This is 0. Why? This is a fixed. So U is horizontal. Let me put U, V, and theta. So U1 is 0, V1 is 0, theta 1 is 0. That's a boundary condition. U3 is 0, V3 is 0. Then V7 is 0. And then U10 and V10 are 0. So this will subtract 3 equations. This will subtract, not 3 equations, 3 unknowns, right? 33 unknowns are there, but here these are all known. So this is not really an unknown. So this will subtract 2 unknowns. This will subtract 1 unknown. This will subtract 2 unknowns. Now let us go to the next level. Now what are they telling? It is assumed that the members are axially rigid. So what it means, you V2 is equal to V1. Why? If V2 is not equal to V1, then this will be extending. This will expand, right? But that cannot happen. It cannot expand or shrink because it is actually rigid. So V2 is equal to V1. V4 is equal to V3. V8 is equal to V7. And V11 is equal to V10. And all of them are zeros. So they are also known. Now, how many equations, how many unknowns you are getting rid of? You can get rid of 4 more unknowns, which are V2, V4, V8, and V11. Now let us go to this level. At this level, what we can say, these members are also actually rigid. So U4 should be equal to U2, U8 should be equal to U4, and U11 should be equal to U8. Otherwise, some of these members can expand or contract. That is also not allowed. So U4 is equal to U2 is equal to U8 is equal to U11. So how many equations I'm getting? I'm getting, so if I know U2, then I know U4, U8, and U11. So this subtracts 3 unknowns, right? Now let us go to this point. At this point, these members are also actually rigid. So V5 is equal to V4 and V9 is equal to V8. So this subtracts another 2 equations. Now comes the tricky part. So what is the condition here? So let us assume this angle is theta. So this is a symmetric structure. Let us take it as theta. Now if I see this, now how many equations, now how many constraints I have removed? So I have removed 3 plus 2, 5, 6, 8, 12, 15, 17. From 33, I have got rid of 17 unknowns because they are determined by the boundary conditions and compatibility conditions. So now I am left with 16 unknowns. But what I have not used yet. So do you think NK is 16? No, because I have still not enforced that. I've enforced all these members are actually rigid, but I didn't enforce that this member is actually rigid. Now let me enforce that also. That is slightly not involved. That's slightly tricky. So let me consider this joint and this member like this. So what are these? 5, 6, and 9. So this is the 0.5. This is the 0.6. This is the 0.9. And this is at an angle theta. Now, if this member should not extend or contract, it means that along this direction, right? Let me construct U dash 6. Let me do a coordinate transformation like this, and this is V dash 6. Similarly, here, let me consider U dash 5 and this as V dash 5. Now, what do I know? U dash 6 is equal to U dash 5. So it is not UV, it's along an inclined coordinate system. So if this is our XY coordinate system, there is some X dash Y dash coordinate system. So in this coordinate system, what I have is U dash 6 is equal to U dash 5. That's all. So this ensures this member is actually rigid. But what this means, now how are U dash and do this related? If you do normal coordinate transformation, you will get that U dash 6 is equal to U6 cos theta plus V6 sin theta. It is very simple. You just take this and resolve it along this directions. Okay, if it moves U6 this way and V5 this way, and this angle is theta, you can find it directly. Similarly, you will have U dash 5 is U5 cos theta plus V5 sin theta. Now these two are equal. That is one constraint. Okay, if these two are equal, what it means? Fine, that is one constraint. Okay. Then what is the other constraint? So if I say these two are equal, then I'll get one equation. What is that equation? One equation and 4 unknowns. So I will get, I'll let it be, right? Let it be. I'll come to it later on. And there is another, so this gives one equation. So let me write it. U6 cos theta plus V6 sin theta is equal to U5 cos theta plus V5 sin theta. Now let me eliminate U6 from this equation. I'll get U6 is equal to U5 plus V5 minus V6 tan theta. So now I got U6. So I can subtract one more unknown. Now let us consider the other member like this. So again here I can set up a local axis like this. So let me call it U6 double dash V6 double dash. So this is another coordinate system. This is V9 double dash Q9 double dash. Same thing. Suppose this makes an angle theta. This also makes an angle theta. So let me take this measured counterclockwise as theta. Same equation you will get that U double dash 6 is equal to U double dash 9. When you do everything, say let this angle be theta double dash. When you do all this, you will get U9. Okay, let us relate this to this. You will get U9 is equal to, because this is first point and this is second point. U9 is equal to U6 plus V6 minus V9, some tan theta double dash, something like that. So in U6 is already known, other things are already known. So this will subtract one more unknown from our list of unknowns. So we had 16 unknowns. These two conditions of actually rigid members reduces two more unknowns. So how many we are left with? We are left with 4 unconstrained degrees of freedom. So these are kinematically admissible. They do not violate compatibility. They do not have any extra constraints, and then they can be arbitrarily specified. So the degree of kinematic indeterminacy for this problem is 16 minus 2, which is 14. Now let's go to the next problem. Determine the kinematic indeterminacy for the following frame, and it is again assumed that the members are actually inextensible. So this is much simpler. Let's start. So what all? So there are not so many members, so it is easier to add than subtract. In the previous case, I subtracted because there are too many members. Here, let me denote the degrees of freedom. So can this move? No, there's no translational degree of freedom. It only rotates. Let me call these points 1, 2, 3, 4, 5. So this can rotate. So there is theta 1. And here it can translate and rotate. So what are the, yeah, that is fine. Here also, here what do we have? Here can it translate? Yes, this can translate and this can rotate. Can it move vertically? No, because we have the constraint V2 is equal to V1, but V1 itself is 0. Since this member is actually inextensible, it cannot extend, so V2 should be equal to 0. So that is not a degree of freedom. For the same reason, V3 is also equal to V5 because the member 3, 5 is actually inextensible. So that is also equal to 0. So this can also rotate. Can it move horizontally? It can move horizontally, but how much is the movement? U3 is equal to U2. So that is not an independent degree of freedom. It is equal to U2, but if we have once determined U2, it is not an independent degree of freedom. So we cannot consider it, we cannot draw the arrow again. And here, U4 is also equal to U3. So you can, that is not an independent degree of freedom, but it can rotate and move vertically. So how many we have? 1. So what are the degrees of freedom? We have theta 1, U2, theta 2, theta 3, theta 5, U5, and then V4 theta 4. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the answer. Now let's go to the next problem. So determine the kinematic indeterminacy of the following beam. Members are again assumed to be actually inextensible and loads are transverse. Now here you will see that some of our shortcuts will break down. So again, let me call this as we call this point as 1, 2, 3. These are internal hinges, 4, 5, and 6. So what are all the degrees of freedom at joint 1? It can move vertically. Can it move horizontally? No, because this beam is actually inextensible. So if there is a rigid wall here, it cannot contract. So horizontally, there's nothing. It can rotate. So we have V1, theta 1. At 2, can it move vertically? No, it can only rotate. So you have the slope theta 2. At 3, there's an issue. It can move vertically, and left side the slope can be different, and right side the slope can be different. Because it is an internal hinge, the slopes don't have to be continuous there. It can move vertically, but left side slope and right side slope can be different because it is just hinged at that. So what are the degrees of freedom there? V3, theta 3 to the left and theta 3 to the right. And at point 4, what do we have? It cannot move vertically. It has to rotate, and the slopes have to be continuous because it is an intermediate support. So at this point, we have V4, theta 4. At the point 5, same condition as 3, can move vertically. Left side, it can have a different slope. Right side, it can have a different slope. So we have V5, theta 5 left and theta 5 right. And at the fixed support, we don't have any degree of freedom. So how many have we got totally? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the answer is option A, 10. Yeah. So let us go to the correct answer is 10. Let's go to sixth problem. Now determine the static indeterminacy of the following frames. So let's check whatever formula we derived and by also systematically examining these. Now if I look at the structure, so let us determine the external indeterminacy first because it's easy. We have 3 reactions on this side and 3 reactions here. So for this structure, NSE is 3 plus 3, 6 minus 3, which is 3. Now, how many member forces we are having? We are having 3 members, and in each of them we have axial force, shear force, bending moment. So in what is internally indeterminate? So there are 3 members, and each of them have 3 unknowns, internal unknowns. And how many equations of equilibrium I can have? I have 1, 2, 3, 4. So internal indeterminacy is I have 4 joints. For each of them, I have 3 equations of equilibrium. But if I consider all 4 joints, then the global equation will also be included. So I have to subtract 3. So how much is this? Degree of static internal indeterminacy is 9 minus 12 minus 3, which is 0. So in for this structure, ns is equal to 0. 0 plus 3, which is 3. So the same thing comes even if we use the formula 3C for internal indeterminacy, because there is no closed loop. It is an internally determinate frame structure, which is a portal. That's all. In this case, what is the static external indeterminacy? We have 3 reactions here, and we have 2 reactions here. So degree of static external indeterminacy is 3 plus 2 minus 3 equation, which is 2. And what is internal? If we see there are 2 closed loops like this. So there are 2 closed loops. So if you use the formula, you will get 3 into 2, which is 6. Or if we use Sumed's approach, right? What did Sumed suggest? 3 into the number of members. How many members are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 members minus 3j minus 3. How many joints are there? 1, 2, 3, 4, 5, 6, 7, 8. Wait a minute. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. 8 minus 3 because that will include the global one. So how many are these? 27 minus 21. So this is another, so this is also 6. So whether you use the number of cuts, a number of closed loops, or this formula, we get the internal indeterminacy to be 6. So totally, ns is equal to 8. So the correct answer is for this structure it is 3, and for this structure it is 8. So the correct option is B. So let me pause here. Kindly let me know if you have got any doubts in what we have discussed up to now. If there are any doubts, I can clarify. If there are no doubts, let me go ahead and finish the other 4 problems. Is this okay? Is everything that I did up to now is okay? Okay, fine. It seems there are no doubts. Let me proceed. So for this problem, determine the static indeterminacy for this truss. So again, this is much simpler. So how many reactions we have? We have vertical reaction, horizontal reaction. Here we have vertical reaction. So externally it is determinate. So NSE is 3 minus 3, which is 0. Internally, how many members we are having? We are having 1, 2, 3, 4, 5, 6, 7, 8, 9 members. So internally, we have 9 members. There are 9 member forces. And how many joints we are having? 1, 2, 3, 4, 5, 6. So at each joint, we have 2 equilibrium equations. So 2j, but I have to exclude the global ones. So how many joints are there? 6 joints. So internally also it is 9 minus 9, 0. So ns is equal to 0. So it is a statically determinate truss. Is this a stable truss? Yes, this is a stable truss. By inspection, by giving a small load perturbation, we can see that it is a stable truss. Now, the same number of members, same size of members, if I do it this way, sorry, let me do it. Suppose same triangle, and say I'm having a similar triangle in width. So this triangle is similar to the outer triangle. And if I connect it this way, so this doesn't change the number of members or the number of reactions. So this is still statically determinate, but is this stable? If you see, if you extend these forces, they meet at a point, right? Which means these 3 forces that are coming externally to the inner triangle are concurrent. So if I apply a small force in this direction, there is nothing that prevents the rotation of the inner triangle with respect to the outer triangle. So if I have a truss made up of similar triangles like this, and they're connected to the vertices in this way by truss members, then it is an unstable truss. But this is a stable and statically determinate truss. So this is just to add to this problem. I felt it's good to know that. Well, let's go to the next problem. This is an interesting problem where we are actually finding the unknown internal forces by the force method of analysis. We have some. So the question seems very big, but basically what it says is use the force method of analysis and determine the unknown reaction Cy. So we use force method of analysis. What is this structure called? It is called a propped cantilever. Propped cantilever B. Now, uh, let us solve this. So, what is the issue here? We have a structure like this. How many reactions we have? We have, okay, there are no horizontal forces, so let's ignore the horizontal part. It has, let us consider only the vertical forces and moments. MA, AY, this is P, this is CY. So how many equations of equilibrium I have? I have ignored the horizontal force. So there are only two equations of equilibrium, which are sigma Fy equal to 0 and sigma moments is equal to 0. And how many unknowns I have? I have three unknowns. So two equations, three unknowns. I have already used one equation. That is, since no forces are horizontal, the horizontal reaction force that is coming here is 0 because sigma Fx is 0. That's all. So there are three unknowns and two equations. So this is statically indeterminate to the first degree. Okay, now let us solve this. So this structure, I can consider it to be a superposition of two structures. How? So let me retain the fixed support as it is. And let me replace the roller with a reaction, that unknown reaction that it supplies. So any Cy that satisfies equilibrium of this is statically admissible. But is it kinematically admissible? Is it compatible? That we have to find out. So this structure, I can decompose into two cases. One where P alone is acting, and the other case where Cy alone is acting. Now, what is the condition that it should satisfy? That is, so it is statically indeterminate to the first degree. We have one unknown reaction, Cy. I want to find Cy. If I want to find Cy, I want one extra equation. I want one extra equation. Who gives that extra equation? This fixed support at C. What is that? Delta C is equal to 0. The displacement of the point C due to the combined action and unknown Cy. Because of this, delta C should be equal to 0. So the Cy that obeys this is kinematically admissible as well as statically admissible. So it is a solution to our structural analysis problem. Now to do this, let us determine the displacement in this case. So here only P is acting at the midspan. So in this, let us solve this problem 1 and problem 2. So if we try to solve problem 1, what do we get? What method we can use? We have four methods of analysis. Let me use the method of let us use the moment area method because it is very simple. We can use any method that you want, or if you have say conjugate beam method, anything is fine. So we have P applied here. What is the bending moment diagram? It looks something like this. Negative. What is the maximum value? PL by 2. Now we want to find the displacement of the point C. So say if we use the conjugate beam method, what does it say? Conjugate beam method says that replace the actual real beam with a conjugate beam such that the loading that comes onto the conjugate beam is equal to the m by EI of the real beam. So since this is negative, this loading should be downwards. And in the conjugate beam, if this is a free end, so moment, sorry. So this is a free end. So moments, shear force, they are all 0. And what is non-zero? The displacements and the rotations are non-zero. So on the conjugate beam, the moments and shear force in the conjugate beam are equal to the displacement in the real. So if I want to get delta C1, it is equal to the bending moment induced in this structure due to this loading, which is PL by 2EI. Now getting the support moment is very simple. What is the total force? It is PL by 2EI acting at L by 2. Since it's a triangle, I will add another half. Where does this act? It acts at L by 2 by 3. So L by 6 from this side. So on this side it is L by 6 into 2, which is L by 3. So L by 2 plus L by 3. So this is nothing but PL cube by 8 into 6, 48. So this is 5 by 6, this is 8, 48. So D1, which is caused by the single midspan load alone, is PL cube by 48 EI. And because of Cy, that is a very simple case, you know, for a tip loaded cantilever, and this is minus or plus? Minus, because this is minus. And what is delta C2? The displacement at the point C due to the force acting at C itself. How much is that? Again, you can do the same thing. For this, the bending moment diagram will be like this. So apply that as load onto the conjugate B. Since here the displacement is non-zero, the moment will be non-zero. For this, if you find out, it will be half into PL by AE, PL by EI, PL by EI, acting at 2L by 3. So yeah, into L by 2 also. There's an L by 2. L, sorry. So the answer is PL cubed by 3A. Sorry, this is not P, this is CY. CY. The maximum is CY into L, because this distance is L and CY acts at this end. So it is CY L cubed by 3EI. So this is upwards because the force is upwards, you know, this displacement is also upwards. So this is positive. Now, what is the compatibility condition for this problem? Compatibility condition is the total displacement at the point C should be equal to 0 because it is supported. But what is the total displacement? Due to principle of superposition, it is delta C1 plus delta C2. What is delta C1? It is minus 5PL cubed by 48 EI. Delta C2, it is CY L cubed by 3 EI. This should be equal to 0, which means CY is equal to 5P by 16. So let us see which answer coincides with this. So CY is equal to 5P by 16. D2 is CY L cube by 3EI, that is what we got. And D1 is PL cube by 4, 5 PL cube by 48. Fine. Now let's go to the next problem. So here we are asked to find out the degree of static and kinematic indeterminacy for this following frame. So as usual, let us do the numbering 1, 2, 3, and 4. What are the unknown reactions? We have say Fy at 1, Fx at 1, and Fy at 4. So external degree of external static indeterminacy is 3 minus 3, which is 0. And internally it is so how many members we have? This is one member, this is one member, this is one member, this is one member. So in each of these members there are 3 unknown forces. So there are 3 n. And how many joints we have? Minus 4 joints. And at each right, there are 3 members. So this is equal to 3n minus 4j minus 3. So there are how many members? 4 members. So 3 into 4 is 12 minus, sorry, 3j minus. There are 3 equilibrium equations that we join. So 3 into how many unknowns we have? How many joints we have? There are 4 joints. Minus 3, which is equal to 3. So the degree of static indeterminacy is 3 plus 0. What are the kinematic degree of degree of kinematic indeterminacy? So how many unknowns we have? Here we have an unknown rotation, horizontal and vertical are fixed. Can this move horizontally? No, because this is actually inextensible. Can it move vertically? No, because there's a support reaction. So this can also only rotate. Here, coming to this point, can it move vertically? No, because this is actually inextensible. Can it rotate? Yes. Can it move horizontally? Yes. At this point, can it move horizontally? Yes, but it is equal to the horizontal displacement of the point 2. So it is not an independent degree of freedom. Can it move vertically? No, this is inextensible, but it can rotate. So we have 1, 2, 3, 4, 5. So nk is equal to 5. So the answer is 8. Now let's go to the last problem for the day. So here, let us determine the deflection at this end. So this is a very interesting problem. So what we have is not a prop cantilever. See, we have something like a prop cantilever, but it is not really a prop cantilever. So we are applying a force P here. There is a spring of some stiffness K. And this is, as usual, beam of length L and cross-sectional properties EI. So this is a very nice problem. Let us see how to solve it. So if it is a prop cantilever, you know what to do. We just solved in problem number 8. If it is a prop cantilever and the load is applied somewhere, you consider how do you do it? You split it up into 2 parts and then you do everything else. But here, in this case, it is not a prop cantilever. So you cannot enforce that VB is not equal to 0. So what is the condition that comes here? So that's a very interesting thing to do. So we can do this problem by 2 methods, but they have said use the force method of analysis, which means the force in the spring should be unknown. So let us assume force in the spring as unknown F. Now, you have a point, right? Let us look at this joint B. So at this point B, what are all the forces that are acting? One is the force that comes from the spring F, which is F. One is the applied force, 50 kilonewtons, 50 newtons. Now let's just take it as P. So this is P. Is there any other force at this joint? At this joint, 2 members are connected. One is the beam, one is the spring, and there's an applied force. So applied force I have shown, the spring force I have shown. There is also the shear force in the beam. So let us take the positive sign convention. If this is the beam, to its left, upwards, right, downwards is our convention, which means on this point B, it will be equal and opposite. So we'll get an upward force of VB. So this is the shear force in the beam at the point B. So this is BB. Now what is the equilibrium equation? Can we determine this force VB? Yes. So VB is equal to P, or normally F plus VB is equal to P, vertical force equilibrium, which means VB is equal to P minus F. So we have determined what is the shear force applied to the beam like this. So this is basically force method of analysis. We have taken an unknown force F, and now we'll solve for that. How do we solve for it? Let us consider the beam subjected to a force Vv, which is P minus F. Which direction it acts? On the beam, it acts downwards. So on the beam, it has a force P minus F. What is the deflection due to this? So the beam will deflect. Let us call this deflection as delta 1. So what is delta 1? We just determined in the problem number 8, if there is a tip load of P minus F acting, delta 1 is equal to, since it is downwards, let me call it minus. It doesn't matter. Okay, let it be P minus F L cube by 3EL. This is what we just found. So this is delta 1. Now the condition is not that delta 1 is 0 because there's a spring. It is not a rigid support. The spring can deform. Now let us look at the spring system. So it is something like this. And there is an internal force of F in the spring. So I have marked it opposite to the direction in the joint. Now, if there is a force F in the spring and the spring constant is K, what is the movement? What is the deformation of the spring? It will be equal to, say, delta 2. Delta 2 will be F by K. I have taken the sign convention in a consistent manner. So here also downwards is positive. Here also downwards is positive. Now let us consider the compatibility condition. What is the compatibility condition in this case? What is the compatibility condition? So compatibility, as I said, is the different parts of the structure should not break away or overlap. So it means this spring doesn't deform something like this. This system doesn't deform in some manner like this. So what it means, delta 1 should be equal to delta 2. So that is our compatibility condition. The displacement of the spring, endpoint of the spring, and the displacement of the endpoint of the beam should be equal. Otherwise, there will be a gap in the structure that is not allowed. So the compatibility condition is delta 1 is equal to delta 2. So basically, F by K is equal to P minus F L cube by 3EI. Now, what is our unknown? F is our unknown. So let us determine F. Let's determine F. Determine F. How to determine F? Just rearrange this equation, right? We'll have F 1 by K. From this side, if we bring everything within this side, we'll get L cube by 3I is equal to P L cube by 3I. And that's it. So let me find what F is. It is nothing but 3PL cube by 3I divided by 1 by K plus L cube by 3EI. So if you simplify this, what you get will be P. So here, if you take LCM, this in both cases 3EI will be common. We'll get P, K goes to the numerator, PK by 3EI plus KL cube. So this is the force that is applied. PK, of course, L cube is there. PL cube into K by 3EI plus KL cube. So this is the force in the spring. We have determined the force in the spring, but what is asked in the question? They're asking the displacement. What is the deflection of the end B? So how do you determine it? The deflection of the end B, right, from our compatibility condition, it is the same as delta 1, which is also the same as delta 2. But what is delta 2? It is F by K, where K is the spring constant. So basically, delta B is equal to F by K, which is this quantity by K, which means this K will disappear. It is nothing but PL cube by 3EI plus KL cube. Let us find out what it is. So delta B is equal to, how much is P? 50 newtons. How much is L? L is 0.2 meters. So L is 0.2 meters cube by 3. E is 200 GPa, so 200 into 10 power 9. I is what? I is given as 416.667 mm cube. So that is 416.667 mm cube. So into 10 power minus 12 plus what is K? K is given as 2 newtons per mm, but you want to get it in meters. So 2 into 10 power 3. And L is again 0.2 the whole cube. So if you solve for this, if you evaluate this, what you get will be 1.5 mm. So the correct answer in this case is C, 1.5. So yeah, we are at the end of today's session. If there's any doubt, you can ask me. I'll stay back for a couple of minutes. Since we have got some more time, uh, let me draw your attention to something interesting. So some insights. So if you look at the last problem we solved, we had something like this, right? And we found the displacement of this point due to an applied shear force of P minus F as P minus F L cube by 3 pi. Now this is nothing. So this you can also write it as, so this is the deflection. This you can write it as P minus F into flexibility F. So basically here, or wait, let me get back to this. We got something like this, P minus F. And we also saw this is equal to what? This is equal to F by K. That is, this comes from compatibility. This is compatibility. And by equating these two, we got something like F into L cube by 3EI plus K is equal to P L cube by 3EI. Now you see what where I'm getting at, right? So this is an unknown. What is the size of this unknown? It is 1. So it is 1 cross 1, you can see. These are some coefficients. So there is one coefficient. So this is also 1 cross 1. And this is some known displacement. Right? So this is also 1 cross 1. So this is in the form Ax equal to B, where A is equal to this. So this is equal to A, this is equal to B, this is equal to X. So this is basically the crux of force method. So this A is called the flexibility matrix. So for this system, the flexibility matrix is given by this one. So for this system, the flexibility matrix is 1 by 1, which is L cube by 3EI plus K. That's it. Wait a minute, not K, K inverse plus K inverse, 1 by K. Similarly, for problem 8, if you see, here what is the system that we got? Here we got something like this. Minus 5PL cube by 48 EI plus CYL cube by 3 EI is equal to 0. We can also rewrite it as L cube by 3 EI into Cy is equal to 5PL cube by 48 EI. Now again, this is the flexibility matrix. This is the unknown, and this is the known displacement quantity. So again, this is of the form Ax equal to B. So this is the force method. So this is flexibility. Yeah, just I felt I should say that. So we are at the end of today's session. Let me wait for a couple of more minutes. If anybody has any doubt, you can ask me. Otherwise, I'll close the session by now. Any doubts? Okay, it seems like there are no doubts. Let me stop the recording. Stopping the recording here. So thank you all for attending. Yeah, this session I could complete on time. This is an easy assignment. So it's basically you have to do the things systematically. Then you will be able to solve all the problems. There is not much calculations involved. So all the best for your this week's assignment. Thank you, everyone. I'll make the recordings available as soon as possible.